Let's dive right into the literal source code of our reality. Today, we're looking at a true mathematical masterpiece. It's a single equation that is somehow both the absolute crowning achievement of human intellect and, as we're rapidly discovering, completely broken.
Every particle you are made of, every force holding your atoms together, every interaction happening inside your body at this exact moment, all of it described by a single equation that fits on one page. It is the most precisely verified theory in the history of science, accurate to 12 decimal places. It predicted particles before we had the technology to find them, and every single prediction it has ever made has been confirmed. There is just one problem. It describes only 5% of the universe. The other 95%, it doesn't even mention.
Part 1, the equation of everything. Take a look at this. This is the Standard Model Lagrangian. It's the absolute pinnacle of relativistic quantum field theory. And yeah, it's a dense, honestly, pretty intimidating wall of math. It's actually so iconic you can buy it printed on a coffee mug at the CERN gift shop. But what this math represents is just profound. See, in this paradigm, particles aren't treated like tiny little billiard balls bouncing around in space. Instead, they're quantized excitations of continuous fields that fill all of spacetime. This one mathematical expression encodes every single known elementary particle and 3 of the 4 fundamental forces of nature. Part 2, decoding the source code. Now, we can actually break down this huge, incomprehensible formula into pieces that make sense for the actual atoms in your body. It's brilliant, really, how 50 years of physics, from Paul Dirac in the 1920s all the way to the Higgs boson discovery in 2012, is neatly organized into 4 functional domains. First, you've got the gauge fields, which basically tell us how the fundamental forces operate. Then, matter kinematics describes how fermions, the matter particles that make up you and me, actually move and interact with those forces. After that is the Yukawa sector, a fascinating piece of math explaining how matter particles couple to the Higgs field to get their mass. And finally, the Higgs potential, describing how the Higgs field interacts with itself. Basically, every subatomic event in the known universe is just a combination of these 4 terms. So why does all this matter to you? Well, because these gauge interactions literally describe everything you experience on a daily basis. Electromagnetism, that accounts for the light hitting your eyes right now and the chemical bonds holding your coffee mug together. The strong nuclear force is that incredibly powerful glue keeping the protons and neutrons inside your atoms from violently flying apart. And the weak nuclear force governs radioactive decay, which is what powers the core of the Earth and the sun up in the sky. All of that is perfectly mapped out by this one equation. Part 3, the pinnacle of precision. Because you have to understand, this equation isn't just some beautiful abstract theory. It's an absolute, invincible fortress of experimental physics. When we test it, it doesn't just pass. It predicts reality to a staggering 12 decimal places of accuracy. The ultimate, most rigorous test of this is something we call the anomalous magnetic moment of the electron. See, classical physics predicted one specific value for how an electron behaves in a magnetic field, but the Standard Model accounts for the crazy fact that empty space isn't actually empty. It's this chaotic vacuum of virtual particles constantly popping in and out of existence in these tiny, incredibly fast quantum loops. Back in 1948, Schwinger derived the very first correction for this, known as the Schwinger factor. Today, physicists are computing these corrections up to 5 loops, which involves thousands of mind-bending Feynman diagrams. And when we actually measure it in the lab, the equation matches physical reality to better than 1 part in a trillion. It's just an absolute triumph of the human mind. Part 4. The 95% problem. But here is the massive twist. Despite this unprecedented perfection, the equation is fundamentally broken. When we look out at the wider cosmos, it completely detonates our confidence in everything we just talked about. Cosmological measurements clearly show that all the ordinary matter, the quarks, the electrons, the gauge bosons, makes up a mere 5% of the mass energy density of the universe. The rest is roughly 25% dark matter and 70% dark energy. And our beautiful, perfect equation, it says absolutely nothing about them. And let's see how this builds into an even bigger problem. The Lagrangian includes electromagnetism, the weak and strong forces, quarks, and leptons, but it completely ignores the most obvious force in our everyday lives, gravity. If you try to force gravity, as described by Einstein's general relativity, into this quantum framework, the math just completely breaks down. It spits out these uncontrollable infinite probabilities that physicists call non-renormalizable. The microscopic quantum world and the macroscopic gravitational world simply refuse to speak the same mathematical language. And the theoretical crises definitely don't stop there. We have the hierarchy problem, where the mass of the Higgs boson is so sensitive to high-energy quantum loops that it requires an unnatural fine-tuning of 1 part in 10 to the 34th power just to remain stable. Then there's the cosmological constant problem, where the equation calculates the vacuum energy of space and gets an answer that is off by 120 orders of magnitude. That is widely considered the most spectacular failure of a theoretical prediction in modern physics. Plus, it can't even explain why there's more matter than antimatter. Ultimately, these crises prove that our beloved Lagrangian isn't the final answer. It's really just a low-energy approximation waiting to be shattered.
Part 5. The 2026 Anomaly.
The thing is, scientists aren't just sitting around waiting. They're actively trying to break the equation. And we might have actually found the crack in an incredibly quirky term called the penguin decay. Researchers at CERN's LHCb experiment released data on these highly rare quantum events. It basically involves a bottom quark inside a B meson transforming into a strange quark, spitting out a kaon, a pion, and 2 muons. Now, in the Standard Model, this specific transformation is forbidden at the basic level. It can only happen through highly suppressed, incredibly complex quantum loops. Well, the LHCb team studied 650 billion of these specific decays, tracking exactly how the particles flew apart.
And guess what? They found that the particles are behaving in ways the equation says they shouldn't. The data shows a statistical tension of 4 standard deviations, or 4 sigma. In plain language, this means there is only a 1 in 16,000 chance that this is just a random statistical fluke. While physics usually demands a 5 sigma gold standard to declare an absolute discovery, this 4 sigma result is supported by independent experiments, strongly suggesting that unknown particles or forces are secretly interfering behind the scenes. So, what exactly is hiding in the quantum loops of those penguin decays? Theorists have 2 leading suspects right now. The first are leptoquarks. These are hypothetical bosons that would completely shatter the classical boundary between matter families, basically allowing quarks and leptons to directly interact. The second suspect is a heavy Bechter boson, often called a Z-prime boson. If this thing exists, it means there's a massive, undiscovered new particle out there introducing an entirely new, 5th fundamental force of nature. And the hunt to prove this is actively unfolding right now. On June 29, 2026, CERN initiated Long Shutdown 3, turning off the Large Hadron Collider for a massive multi-year upgrade. By the 2030s, it's going to reboot as the High Luminosity LHC, using state-of-the-art 12 Tesla superconducting magnets to smash protons with unprecedented intensity. Looking even further ahead, Europe is pushing for the Future Circular Collider, a massive 91-kilometer ring designed to test these exact anomalies with razor-sharp precision. We are literally rebuilding our tools from the ground up to chase this ghost in the machine.
Which leaves us standing on the thrilling precipice of the unknown. We've pushed the Standard Model Lagrangian to its absolute limits. Sure, it's given us a 12 decimal place understanding of our immediate reality, but it leaves 95% of the cosmos in total darkness. The cracks are forming. The anomalies are piling up. So I want to leave you with this one thought to take away. When the most successful theory in human history finally falls, what replaces it?